Imagine for a second that you are looking at the raw data feed from a commercial airplane wing mid-flight.
Oh, that is just a staggering amount of data.
Right. I mean, we're talking about thousands of sensors. You got, strain gauges, piezoelectric monitors, and they're all updating continuously as the plane just punches through a massive thunderstorm.
Yeah, it's an incredibly chaotic system to try and monitor.
Exactly. You've got sheer winds hitting the side and the massive weight of the jet engines pulling down, forward thrust, and just chaotic turbulence tossing the entire structure around.
It's basically a storm of interacting physical forces.
And the data output from that wing is just this massive, continuously shifting matrix of numbers representing all of that. Which brings us to our mission for today's deep dive.
Right. We need to figure out how engineers actually filter all that chaos into actionable physics.
Yes. And to do that, we are digging into a really fascinating technical module. It's titled Day 8 Matrix Decomposition, Theory and Code.
It's a great source.
It really is. Wasn't a look at how a very specific mathematical theorem takes what looks like super dense, abstract, linear algebra and essentially translates it into the physical language of the universe.
Yeah, the focus here is really on bridging that theoretical math with physical reality.
And we'll be looking at, aerospace engineering, complex electronics, and even the kinematics of robotic arms. But for you listening, don't worry, you won't need a calculator for this.
Definitely not. We aren't just going to sit here and look at the dry algebraic rules of matrix operations. We really want to explore the underlying causality.
Right, the why behind the numbers.
Exactly. We need to understand the mechanism of how this specific mathematical tool brings order to the chaotic physical systems you were just describing.
Okay, well, let's start with the core operation from the source material. We're dealing with square matrices.
Yes, square matrices.
And specifically, something called the transpose operation, which is denoted by adding a little superscript t to the matrix.
Right, and the transpose simply involves swapping the rows and the columns across the main diagonal.
But, rather than just looking at it as randomly moving numbers around a grid, the text focuses heavily on the structural symmetries that this operation actually reveals.
Because the structural implications are really everything here. I mean, when you swap the rows and columns, you are essentially testing the matrix for inherent balance.
That's to get for balance. I like that.
Yeah, and the source introduces two critical states based on this test. First is the symmetric matrix.
Okay.
That's where the matrix remains completely unchanged after you transpose it. So A transpose equals A.
Got it.
And then the second state is the skew symmetric matrix. That's where transposing the matrix results in the exact negative of the original matrix. So A transpose equals negative A.
Okay, so if we try to visualize that transpose operation, it's kind of like folding a square grid of paper perfectly diagonally, right? Like from the top left down to the bottom right.
That is a perfect way to visualize it.
So for the symmetric matrix, that means the ink numbers on the top right perfectly match the ink numbers on the bottom left when they touch.
Exactly. They mirror each other perfectly.
But for the skew symmetric matrix, everything that folds across that diagonal crease becomes its exact mathematical opposite.
Right.
So like a +5 on the top right lands directly on a -5 on the bottom left.
Yes, and if you follow the algebraic logic of that fold to its absolute conclusion, you uncover what is really a foundational property of the skew symmetric matrix.
Wait, hold on. Let me think about this fold analogy for a second. Because what happens to the values that sit exactly on that diagonal fold line?
Well, they don't move.
Right. They don't move when you transpose the matrix. They stay exactly where they are. But the rule for a skew-symmetric matrix dictates that every value must become its negative self after the transpose.
Exactly.
So looking at the algebra, the value on the diagonal must equal its own negative. But wait, the only number in the mathematical universe that is equal to its own negative is 0.
You nailed it. The result is a main diagonal consisting entirely of zeros.
Wow. Okay.
And this isn't just some fun quirk of algebra. It represents a very profound physical reality.
How so?
Well, in physical systems, the main diagonal of a matrix almost always represents self-interaction, or like direct localized scaling.
Okay, meaning what exactly?
It means a strict zero diagonal proves that a skew-symmetric matrix inherently lacks that type of self-referential value.
Oh, I see.
It represents pure relational interaction between different elements, completely without affecting the element itself. And that becomes incredibly vital when we try to isolate different physical forces.
Which leads us directly to the central mechanism of the text, right? The decomposition theorem?
Yes, the decomposition theorem.
And the theorem basically states that absolutely any square matrix-like, no matter how messy or chaotic the data is, can be uniquely broken down into the sum of two parts.
Any square matrix, yes.
One perfectly symmetric matrix, which we'll call P, and one perfectly skew symmetric matrix called Q. And the text provides this remarkably simple algebraic formula for this. To find P, you just take 1/2 of the original matrix plus its transpose, and then to find Q, you take 1/2 of the original matrix minus its transpose.
It is a beautifully elegant identity. You have P plus Q, and when you combine those two equations, the transposes just cancel out, and you are left with your original matrix.
Which is super satisfying. I mean, I completely understand the algebraic neatness of the identity. Mathematically, it works perfectly on a chalkboard.
It does.
But, practically speaking, what does adding half of a matrix to half of its transpose actually accomplish physically? Like, why do engineers go through the effort of doing this specific algebraic split?
What's fascinating here is that to understand the utility, we really have to recognize that the original matrix often represents superimposed physical phenomena.
Superimposed, so stacked on top of each other.
Exactly. In the real world, physical forces rarely happen in isolation.
Right.
When you take the sensor data from your airplane wing, that single data point is a tangled mess of different behaviors happening at the exact same millisecond.
Okay.
The decomposition theorem serves as a mathematical filter. By isolating the P and Q components, it mathematically separates the data into fundamentally different physical behaviors.
All right.
Yeah, behaviors that are governed by entirely different physical laws.
So it's essentially untangling the data.
Yeah.
That makes the transition into the text's first application domain make a lot of sense. The aerospace engineering section.
Yes, that's a perfect example.
The source talks about using this theorem on something called the displacement gradient tensor. So I assume this tensor is our original chaotic matrix, right?
That's right.
It's capturing every single millimeter of movement happening on that wing structure during the storm.
Exactly. And when an aircraft wing is battling severe turbulence, two highly distinct mechanical phenomena are acting on the metal simultaneously.
Okay, what are they?
The first is actual mechanical strain. So the aluminum or composite material is actively stretching, compressing, and shearing.
Like the molecular bonds are actually being tested.
Yes, physical deformation.
Yeah.
But the second phenomenon is rigid body rotation. Well, a vortex of air might cause a section of the wing to locally pivot or just shift its spatial orientation entirely.
Ah, okay. So the rigid body rotation is just movement through space,
Correct.
to use a biological analogy.
Yeah.
It's kind of the difference between twisting your arm until the muscle physically stretches and burns. That's the mechanical strain.
Yes.
Versus keeping your arm completely stiff and just rotating it in a circle from your shoulder joint.
That's exactly it.
Like in that second scenario, your arm is moving through three-dimensional space, but the tissue itself isn't undergoing any actual stress or deformation.
And that distinction is the entire reason engineers rely on this math.
Really?
Oh, yeah. The original displacement gradient tensor captures all of that movement, the muscle twisting and the shoulder rotation combined into one single clump of data.
Oh, I see. And the decomposition theorem isolates them.
It does, and based on the symmetric properties we discussed earlier, the symmetric component P tracks pure deformation.
The mechanical strain.
Yes. The actual stretching and shearing forces that are actively threatening the structural integrity of the wing.
Okay.
Conversely, the skew symmetric component, Q, mathematically isolates the rigid body rotation.
Wait, I want to unpack the causality there for a second. Why exactly does the skew symmetric matrix isolate the rotation?
Well,
Is it tied back to that zero diagonal we talked about earlier?
it is directly tied to the zero diagonal. Remember that the diagonal values in a structural tensor represent normal strain.
Right, the literal stretching or compressing along an axis.
Exactly. So because the skew symmetric matrix mathematically forces its diagonal to be zero, it fundamentally cannot represent stretching.
Oh, wow.
Yeah, it mathematically guarantees that the object's volume and shape remain completely constant. Therefore, the only movement it can possibly represent is pure rotation.
That is just fascinating. So the basic algebraic rule that a value must equal its own negative making it zero is the literal reason an engineer can isolate the harmless spinning from the dangerous stretching.
It is. And if they couldn't separate them, the raw data would be dangerously misleading.
Because it would just look like a massive movement overall.
Exactly. If an aerospace engineer looks at the combined matrix without decomposing it, the total magnitude of movement might suggest the wing is experiencing catastrophic deformation.
When in reality, it might just be fine.
Right. A huge portion of that movement might just be harmless pivoting in the air current. Decomposing the matrix is basically how you predict metal fatigue accurately and, keep the wing actually attached to the plane.
Yeah, pretty important stuff. And that actually makes the transition to the next domain in the source text really intriguing.
Electronics.
Right, because if the skew symmetric matrix isolates harmless rotation in a physical chunk of aerospace metal, how does that concept of movement translate when we swap physical metal for electrical current?
Well, the physical medium changes entirely, but the underlying mathematical logic remains constant.
How so?
In mechanics, the theorem isolated physical deformation from physical rotation, but in complex multi-port electrical circuits, it isolates passive sharing from active directing.
Okay, the text mentions applying this to impedance matrices, denoted as Z, or admittance matrices, denoted as Y.
Yes, those matrices track how voltage and current relate to one another across all the different nodes in a circuit.
And when energy flows through a really complex network, you obviously have various components interacting.
Right, and when we decompose these impedance or admittance matrices, the symmetric component, the P matrix, isolates the reciprocal network properties.
Reciprocal meaning what energy can travel both ways equally.
Precisely. This represents the passive components of the circuit, things like resistors, standard capacitors, inductors.
Okay.
In these elements, the power transfer is completely bilateral. If you apply a specific voltage from node A to node B, you get a certain current. And if you reverse it and apply that exact same voltage from node B to node A, you get the exact same current.
So it's totally symmetrical.
The relationship is perfectly mirrored. Which is exactly why it maps so perfectly to a symmetric matrix.
So it's kind of like a standard two-way residential street. Traffic just flows in both directions with the exact same ease.
That's a great way to think of it.
But then the text introduces the skew symmetric component, Q, which represents the non-reciprocal behavior.
The active components, yes.
Right. It lists things like gyristors, circulators, and certain amplifier setups.
And these components completely disrupt that bilateral flow. They take the electrical energy and force directional routing.
Okay, so to stick with the traffic analogy, the skew-symmetric matrix represents the aggressive traffic controls.
Yes.
It's like the traffic cop, or the one-way street sign, that forces cars down a highly specific path and explicitly forbids them from flowing backwards.
Exactly.
But again, I want to know how the math actually dictates this.
Well,
why does skew symmetry suddenly mean forced direction?
Think about the properties we already established. In a purely skew symmetric admittance matrix, what do we know about the diagonal elements?
They're all zero.
Right. And in an electrical network, a diagonal element represents a node's self-admittance.
Meaning its direct connection to the ground.
Yes, or its internal dissipation. So if the diagonal is forced to zero, it means this specific idealized component doesn't interact with itself or bleed any energy to the ground.
Oh, so all the electrical behavior is happening strictly in the off-diagonal numbers.
Exactly. And because it's skew symmetric, an off-diagonal value from node A to node B might be, say, perfectly positive.
Okay.
But the return path from B to A is perfectly negative.
Ah, I see.
This indicates a strict phase shift or directional enforcement. The math perfectly describes an active component that takes an incoming signal and shunts it entirely to the next node without allowing any of it to reflect backwards.
Which would be crucial in something like, say, a satellite.
Oh, absolutely. If you are designing a communication circuit for a satellite, you absolutely cannot have the high-power transmission signal bleeding backwards into your highly sensitive receiving antenna.
Right, you would completely fry the satellite's own sensors.
You'd destroy a multi-million-dollar piece of equipment. So the symmetric matrix maps out where the energy is sharing naturally, and the skew-symmetric matrix gives the engineer the exact map of where the network is forcefully directing the signal.
Wow. Okay, so we're seeing a real universal pattern here.
We really are.
The symmetric part is basically the natural balanced state, whether that's structural strain or passive electrical flow.
Right.
And the skew-symmetric part is the relational, rotational, or directional state. And the source material actually scales this up into a third major domain.
Computing and robotics.
Yeah. Moving from directing electrical current to processing data and dictating the physical movement of robotic joints.
It's a really brilliant leap.
The first example in this section is fairly straightforward, based on what we've already learned. In data structures, when you are mapping out network graphs, an undirected graph results in a perfectly symmetric adjacency matrix.
Right, and that maps directly back to your two-way street analogy.
Okay.
If node A is friends with node B on a social network, then node B is equally friends with node A. The data relationship is inherently reciprocal, so the matrix representing it is perfectly symmetric.
Right, that makes total sense. But then the text quickly pivots into something much more complex.
Yes, it does.
It dives into computer vision and kinematic robotics, stating that skew symmetric matrices act as and this is a, quote, cross-product operator matrix.
That's right.
And it says they are heavily utilized to convert angular velocity vectors into infinitesimal rotation matrices.
It's a mouthful, I know.
It is. And I really want to break down the mechanism here, because what exactly does a cross-product operator matrix do to control a robotic arm on an assembly line?
Okay, to understand this, we have to look at how a computer simulates 3D space in the first place. Okay.
When an industrial robotic arm needs to pivot to, say, weld a car door, the software controls that physical movement using an angular velocity vector.
Which is essentially just an arrow pointing in the direction of the axis of rotation, right?
Exactly.
And the length of that arrow tells the system how fast the joint actually needs to spin.
Correct. But here is the major computational problem. You cannot simply multiply a 3D coordinate by a simple arrow vector to get a new 3D coordinate.
You can't.
No, the math just doesn't work that way. To actually calculate the new position of the robotic arm's mass in three-dimensional space, that angular velocity vector has to be transformed into a matrix operation.
Oh, I see.
Specifically, it has to become a rotation matrix.
And so the cross-product operator is the specific tool that makes that transformation.
Yes, exactly. When you take the cross product of the angular velocity and the position vector, you are calculating the instantaneous linear velocity of that specific point in space.
And geometrically, the cross-product operation can be perfectly rewritten as multiplying the position vector by a skew-symmetric matrix.
Wait, really? So the computer basically takes this simple vector, the little arrow, and mathematically expands it into a full skew-symmetric matrix.
Yes.
But why does it absolutely have to be a skew-symmetric matrix? Like, why not any other kind of matrix?
Well, think back to the aerospace wing we talked about.
Yeah.
What did the skew-symmetric matrix mathematically guarantee?
It guaranteed pure rigid body rotation.
Right.
Because the main diagonal was forced to be zero, there's zero switching or deformation allowed in the math.
And that is the exact same mathematical law keeping your robotic arm intact.
Oh.
Yeah. When the computer applies a rotation matrix over tiny time steps, which is what the text calls an infinitesimal rotation, it relies entirely on that skew-symmetric property.
Wow.
If the rotation math contained even a tiny fraction of a symmetric component, the digital model of the robotic arm would mathematically try to stretch, warp, or squash as it moved.
That is wild. So the metal arm would physically try to tear itself apart to follow the corrupted mathematical instructions.
Exactly. Or, think of it in terms of a video game engine.
Okay.
If this math was wrong, a character's arm would suddenly stretch out like a piece of spaghetti when they swing a sword.
That would be a glitchy game.
Right. So by forcing the angular velocity vector through a purely skew-symmetric operator matrix, the kinematics engine mathematically guarantees that the distance between any 2 points on that robotic arm remains perfectly constant while it spins.
It basically preserves the rigid geometry of the object during movement.
Precisely.
It really is incredible how universal this is. I mean, the exact same algebraic quirk that ensures a satellite circuit only flows in one direction is the exact same quirk that allows a robotic servo to spin smoothly without trying to stretch the steel attached to it.
It's all connected by the decomposition theorem.
The theory really is beautiful in its universal application. But, the source text actually makes it a point to ground all of this entirely in modern engineering practice.
It does, yes.
It concludes by moving away from all these chalkboard derivations and gets straight into computational verification.
Yeah, the final section of the module introduces a Python script.
Yes, and the code uses libraries like NumPy to initialize just a completely random, chaotic square matrix.
Just a total jumble of numbers.
Exactly. And then it uses the decomposition formulas we discussed earlier to extract the P and Q parts.
Right.
And then it programmatically validates that P is indeed equal to its transpose, and that Q is equal to its negative transpose with a main diagonal of zeros.
It is a really critical inclusion in the text. It essentially transitions the reader from being a theoretic mathematician to being a practical engineer.
But I actually have a question about the necessity of this step. If the decomposition theorem is mathematically proven-like, if the algebraic identity we talked about is an absolute fact, why do engineers need a Python script to verify it?
That's a fair question.
Right, like, why test it with random numbers if we already know it's universally true?
Because analytical proof on a chalkboard and numerical stability inside a computer are two very, very different things.
How so?
In the real world, simulation software doesn't use perfect fractions. It uses floating point arithmetic.
Oh, meaning there are rounding errors when the computer calculates massive numbers of decimal places.
Exactly. When you are running a finite element analysis on a commercial aircraft wing, you are processing millions of matrices simultaneously.
Yeah, the scale is massive.
And if a single floating point rounding error causes the skew symmetric matrix to accidentally gain even a tiny non-zero value on its diagonal?
Oh, wow. The simulation will actually introduce artificial strain into the digital wing.
Exactly. The Python verification script isn't just proving the math is true in theory. It is proving that our digital tools can calculate the math flawlessly within the strict bounds of computer memory.
So it's basically the computational bedrock.
Yeah.
It's checking that the translation from pure theory into digital processing hasn't corrupted the physics.
Right. An engineer doesn't trust a multi-million-dollar surgical robot just because the algebraic identity looks neat on paper.
Obviously not.
They trust it because the computational physics engine driving it has validated those exact symmetric and skew symmetric properties a billion times over across highly randomized inputs without a single failure.
The code proves the theory is robust enough to actually build our physical world on top of.
It does.
It takes the abstract and makes it load-bearing.
That's a great way to put it.
So, to pull all of this together for you listening, we started with a chaotic grid of sensor data.
A total mess of numbers.
And we saw how a seemingly simple operation transposing rows and columns can reveal the inherent symmetries of the physical world.
Right.
By applying the decomposition theorem, we can split any complex system into its fundamental parts. The symmetric half decodes the structural stretching of aerospace materials and the passive bilateral sharing of electrical currents.
And then you have the skew symmetric half.
Right, which, with its strict zero diagonal, decodes the rigid spinning of robotic kinematics and the forced directionality of active satellite circuits.
It is just a massively powerful framework. The math basically acts as a scalpel, perfectly separating the superimposed behaviors of physical reality into distinct governable laws.
And honestly, exploring how that mechanism works leaves me with a final thought to consider.
Oh.
Yeah. If the most chaotic, randomized systems in the mathematical universe can be perfectly balanced into a symmetric part and a skew symmetric part, separating the natural reciprocal behaviors from the forceful directional ones.
Right.
What other complex, seemingly chaotic systems in your own life or work could be suddenly understood if you just found the right logical lens to isolate them into their fundamental components?
That is an excellent framework for tackling complexity in any field, really.
It really is. Thank you for joining us on this deep dive into the architecture of the physical world. Keep questioning the chaos.